Tampa, Florida. It is 12 noon on a very cold December day. The ambient temperature is exactly 16 degrees Celsius. Detective Taylor has a body and a list of suspects, but he's missing the most important variable. One suspect has a confirmed alibi starting at 10 a.m. Witnesses saw him at a diner across town. To know if that alibi actually matters, Taylor needs to know if the victim was already dead before the breakfast rush started. In forensics, the time of death is the only objective way to test a suspect's timeline. If the math doesn't match the story, the alibi vanishes. Taylor takes his first measurement at noon. The victim's body temperature is 34.5 degrees Celsius. He returns from lunch at 1 p.m. and takes a second reading. The temperature has dropped to 33.7 degrees. You might try to solve this with a simple subtraction, a 0.8 degree drop in 1 hour. But if you try to rewind the clock using that straight line logic, your results will be wrong. This chart shows why a body doesn't cool at a constant rate. Thermodynamics is nonlinear. The rate of cooling is aggressive when the body is hot, but it slows down as the temperature approaches the 16-degree baseline of the room. To reverse engineer this curve, we need a first-order differential equation, a formula designed to track how a quantity changes when its rate of change is also shifting. Newton's law of cooling states temperature change is proportional to the difference between body heat and the room's temperature. We define Tm as our constant ambient temperature, 16 degrees. Rewriting this isolates two constants, K and C, defining the exact thermal footprint of the scene. To find them, we use an integrating factor. An integrating factor is a mathematical term we multiply into the equation to make it possible to solve using standard calculus. By solving for K and C, we are essentially calibrating a mathematical engine to the exact conditions of this crime scene. We run the clock forward first. By plugging in our two readings, noon and 1 p.m., we can solve for our missing constants. Our calibrated equation, T of t equals 18.5 e to the negative 0.044 t plus 16, maps how this body lost heat. To find the moment of death, we set the target temperature to a living human's 37 degrees. Finally, we isolate t to calculate the exact hour since death. The result is negative 2.9. This means the cooling process began exactly 2.9 hours before Detective Taylor took his first reading at noon. The time of death was 9:06 a.m. Because that suspect was only seen at the diners starting at 10, the math has just removed his window of innocence and invalidated his alibi. This equation is more versatile than just a tool for forensic detectives. If we swap the temperature variables, the same mathematical logic holds up. In biology, we use this model for exponential growth. By tracking population instead of heat, the equation dP dt equals Kp can predict exactly when a culture of 400 bacteria will grow into a colony of 2,000. In physics, we use it for exponential decay. It allows us to calculate the 3.3-hour half-life of a radioactive isotope like lead-209 as it sheds mass over time. Whether it's a cooling body, a growing colony of bacteria, or a decaying atom, the underlying mechanics of change are identical. This same math even governs the invisible movement of electricity. Gustav Kirchhoff developed laws to describe the voltage drop in a circuit. He used these equations to track how a battery's energy moves through an inductor, which stores energy in a magnetic field, and a resistor, which limits the flow of current. Kirchhoff's linear differential equation for current is structurally the same as the formula Detective Taylor used to solve the murder. First-order differential equations provide the framework for understanding any system in flux. They give us a way to quantify the relationship between what a system is now and how fast it is becoming something else.